est à l'université Paris-Saclay. Alors pour ceux qui connaissent ou pas Anu, c'est quelqu'un d'extrêmement modeste, mais ce qui ne l'empêche pas d'avoir un parcours académique assez exceptionnel. Donc j'ai juste noté quelques brèves. Donc tu commences ton parcours en physique à l'IIT de Kanpur en Inde. Et ensuite, tu vas faire toute une éducation et un début de carrière, on va dire, aux États-Unis, avec des très grandes universités, donc Yale par exemple, Brown ou Rutgers University, UCLA. Donc, tu développes des travaux sur, principalement au départ sur les mécaniques statistiques, que tu vas ensuite appliquer dans des modèles désordonnés, donc bien sûr sur les glaces de spin. Ensuite, dans les alliages avec les interactions RKKY par exemple. Euh, Tu as travaillé avec des grands noms, même qu'on connaît même pour la jeune génération comme moi. Donc, on peut citer Kosterlitz, Orbach ou Abrahams, par exemple. Et c'est en 1990, je crois, que tu arrives en France à l'école polytechnique. Et puis, dès 91, que tu es embauché en tant que professeur à l'université Paris-Sud. Et maintenant Paris-Saclay. Voilà, donc on peut peut-être peut-être un petit peu général dire que tu es globalement une théoricienne de la matière condensée. Je pense qu'on pourrait, sans trop de résumé, et que ton travail a principalement consiste à modéliser les propriétés des systèmes complexes en général, avec en particulier les propriétés électroniques et magnétiques des quasicristaux, qui reste un objet d'étude très important pour toi et pour la communauté. Et c'est ce dont tu vas, je pense, nous parler en détail aujourd'hui. Merci.
Bonjour. Bonjour à tout le monde et merci beaucoup Edwin pour l'introduction, trop gentil. Je me proposais de faire le talk en anglais parce que bon, j'ai un visiteur et peut-être d'autres ici dans la salle. Si ça ne pose pas de problème. Donc, est-ce que ça vous va en anglais alors? On bascule. Alors, donc, j'ai en anglais, donc, il y a sur la veste. Voilà, je, je m'en doutais un peu. So it's a very great pleasure to give this talk on quasicrystals, which have occupied my large part of my career, not 100%, but a large fraction. And thanks very much to all the organizers and to you for attending. I have planned an introductory talk, so but you can ask questions at any time. Feel free. Now, any talk on quasicrystals tends to begin with this slide showing the Nobel Prize attributed to quasicrystals in 2011. It was a chemistry prize, and it was given to Daniel Shechtman. And Daniel Shechtman is, if the pointer, okay, so, there we are. So the young man there, and he had been working on aluminum manganese alloys. I think the story has been told many times that he saw this kind of electron diffraction pattern with tenfold symmetry, and he noted it in his lab book and with question marks because this is a forbidden symmetry in periodic systems. And this gave rise to many years of quite acrimonious debate. And in the end, the matter was settled, and quasicrystals are now accepted as a new category of matter. So this led to the redefinition of the term crystal in physics. So a crystal is a structure with a sharp diffraction pattern. It has Bragg peaks, and they form a lattice. Okay, so there are two broad categories of crystals. They're the usual crystals we all know before. They are the periodic crystals. They have a diffraction pattern, which is defined on a lattice called reciprocal lattice, which has the same dimensionality as the crystal, 1, 2, or 3 dimensions. A quasicrystal has a diffraction pattern, and the Bragg peaks are in a higher dimensional lattice. So I will give you an example in just 2 minutes. So the quasicrystal is incompatible with translation invariance. It's a different kind of ordering. Okay? And this kind of thing had been already rather incredibly known before in the case of the Penrose tiling. Penrose invented it as a theoretical object, but this is an example of the second kind of quasiperiodic structure. I should say before I start that this lab was involved in quasicrystals research right from the beginning, thanks to Jacques Friedel in particular. He was very fascinated by the stability of these structures and theories, but the older members in the audience may recognize many of these faces. I've put down a few names, probably not a complete list, but they studied X-ray diffraction, thermodynamic properties, magnetism by NMR, transport, okay, a variety of topics. And then the activity has resumed in the last several years, but this time in AX 3. And AX 3, so the people involved are studying soft particles, self-assembly of particles. Okay, so these are experimental and theory colleagues. You also may recognize all these faces now. And we should particularly mention the students and postdocs who contributed a great deal to all this research. And in parallel, there has always been an ongoing work on electronic properties with my colleagues, Pavel Kalugin and Frédéric Pichon. And this is the part I want to talk to you about. But rest assured, the soft matter community may also have some take-home message in the course of the talk. So finally, here's the plan. So I would like to introduce quasiperiodic structures. That, by the way, is just a picture of a real quasiperiodic alloy. You see it has nice pentagonal facets. The next part, I will discuss the quantum states and talk about some experimental measurements interesting to interpret. Then I will probably, unfortunately, not have time to talk about topological aspects, but I have a few slides about that. It's a very active topic. It needs a separate lecture all to itself. And new directions, which are fun to see. Okay, we'll mention a few novelties. Okay, so let's start. Introduction to quasicrystals. I told you about this higher dimensionality, right? So there's hidden dimensionality in quasicrystals. To illustrate, I have this picture of a cube artist that you've probably heard of, Georges Braque, and he was interested in portraying 4 dimensions in his paintings using the cubist technique. So along with Picasso and others. And so this is for him, the 4th dimension was time. And looking at the same object from different angles, different cross sections. But what about now in physics? So in physics, I told you that the Bragg peaks are indexed by some higher dimensional lattice. And here is a complicated figure, you know, so the 5-dimensional cube was projected onto the plane. And instead of talking about this figure, let me tell you about a simpler structure, namely this Penrose tiling. You have already seen it before. It has 2 tiles, a thin tile, a thin rhombus, and a fat rhombus. Now, this is all from an old paper from the 80s by Alan McKay. So he puts a disk on every vertex, call it an atom, and calculate the optical diffraction pattern. And you can see spots, complicated arrangement of spots. Let's zoom in the middle of this picture. Okay, this. You see a large number of spots, and so let's try to index them using some basis vectors. Introduce A1, A2, A3, A4, which are inclined by 2 pi over 5. And you have this last vector A5, I forgot to put its label. A5 is a linear combination of the previous four, right? So with these 5 vectors, you have a 5-fold star, and if you include the time reversed minus k, you have a 10-pointed star. These are the 10 blue points, which correspond to going 1 unit along each of these 10 directions. If you take a combination of 2 successive vectors, you get the green dots. So you can index them. Okay, the indices are these 4 integers, counts the number of times you go in each direction, A1, A2, A3. Orange ones, you have 3 steps, 3 vectors adding to give you the orange dots, and you can subtract. Obviously, you can add and subtract, and in the end, you fill the plane. Okay, but so yes, the diffraction pattern is very complicated. But there are main spots and there are much weaker spots. So usually you take into account the main spots in building a theory. Now these 4 basis vectors here are projections of the 4 axes of a 4-dimensional cube. So you have the 4-dimensional basis, everything is orthogonal, and then if you incline the 4-dimensional cube, you will get something like this. Okay. So we have a crystal in 4 dimensions, which explains the structure of this diffraction pattern. And this is the idea behind a method to get quasicrystals called the cut and project method. So here's a quick cartoon of it. It was introduced independently by all these people, including our colleague Pavel, if he's here, and with Kitev and Levitov. And just next door, there was Duno and Katz in Palaiseau. They're here. And standing with Denis Gracias, who was one of the co-authors of that first important paper on quasicrystals. So these people all had the same idea. You go to the higher dimensional space, consider a strip, an infinite strip, infinite along this direction, which is inclined at some irrational angle. If you project the points within the strip, you generate something which never repeats, with the quasicrystal. Perpendicular to the quasicrystal is the projection of the strip, which is forms in some compact domain, just symbolized by that object, orange. Let me show this example, which is, again, standard for explaining the cut and project method. So let's project from the 2 dimensions to 1 dimension. So everybody knows how to draw a square lattice, has axes, x and y axes, and my strip is this band, which is inclined with a slope of 1 over the golden mean. I will explain more about the golden mean in 2 minutes. But the strip also is the projection of 1 unit of this lattice. So it has some width along this y prime axis. Okay, so now these are the selected points. I've joined them with a blue line. You can put atoms on them. Okay, let's pretend every vertex has an atom. And you project these atoms onto your x prime axis, like so. And what you see is this quasicrystal in 1 direction, right? The x prime axis direction. And you have only 2 possible distances, a long and a short distance. And it's, following some sequence. And this thing has a diffraction pattern. I won't prove it, but you can imagine it's obtained from a square lattice. The peaks can be indexed by 2 integers. Okay? So this thing is called a Fibonacci quasicrystal. Why? So let me explain about the Fibonacci numbers. All right, so the same structure can be obtained in a different way by a concatenation method. Concatenation just means you take 2 things and put them side by side. So I start with a tile which I call the B tile, which is a short segment, an A tile, which is a longer segment, and put them together and make AB. Concatenation. So next step, I concatenate the 2 previous ones. So I get ABA and so on and so forth. And in the limit, infinite limit, I get back that quasicrystal that I showed you earlier. And the Fibonacci recursion formula. You can maybe see it already. If you call the number of tiles Fn, then at the n plus 1 level, the number of tiles is equal to the sum of the previous two chains, right? These chains, by the way, are called approximants because they provide a way to approximate the infinite system. You can do calculations with these small systems and let the size go to infinity. Typically, that's what you do in theories. So the Fibonacci recursion relation, you see that it yields these. You start with the initial conditions, say 0 and 1. Then you repeat this and you get 2, 3, 5, 8, and so on. Okay. And these are the numbers that you see in this book that Fibonacci authored back in 1202. So he was a mathematician born in Pisa, and he actually had an important contribution in his city's life. And he introduced Indo-Arabic numbers to business accounting because he had been in North Africa and his father was a businessman. And that must have been a real shock de simplification because they were using Roman numerals to do their accounting, right? So the Fibonacci did a great service to those people. So this is his tomb. If you go to Pisa and visit the Leaning Tower, it's next to it is a cemetery, and with this nice statue of Fibonacci. Now, one more thing I should say, there's yet another way to get the Fibonacci chain by inflation, where every step you replace a B tile by an A tile, replace an A tile by AB. You keep doing this, you get all those chains again. And I didn't mention it, but the ratio of two successive Fibonacci numbers, it's easy to show. It tends towards this golden mean that I had mentioned earlier. Okay, and the golden mean appears everywhere in quasicrystals, okay? Not just in geometry, sometimes also in electronic properties. Okay, so I think we're all ready to go. You can do the same thing to get other tilings. For example, projection from 4D, you can get the Penrose or the Amann-Bienke tiling, which has different symmetries because the orientation of the strip is different. You can get from 6 dimensions to this 3D tiling. So I think we're ready to start the chapter on quantum states and physical properties. So since the early days, this question has been always asked. If you take models for an electron in a quasicrystal, what kind of eigenstates do they live in? Like, do they have block-like extended states? Or are wave functions more power law-like, as in fractals? And quasicrystals are self-similar objects. You know, you saw the inflation rules, so there is some self-similarity. Or are they just localized like for random systems, right? So these are the questions that are still not completely understood. But I'm going to show you some simple examples and hopefully give you a flavor of what kind of states to be expected in a quasicrystal. So let's do that one-dimensional case again, the Fibonacci chain. You have these hopping amplitudes only. Okay, really the first step is to take this hopping Hamiltonian. You have Ta for the A bond, Tb for the B bond, and you try to ask, okay, what can you say about the eigenstates? Okay, this is the Schrödinger equation. And what this does, when you project it onto the sites, I think everybody has done this in the solid state class, I hope. So you have a relationship between 3 consecutive sites on the chain, the sites J plus 1, J, and J minus 1, right? And related via the energy value. So I'm going to discuss a special situation with 0 energy state and just do the periodic chain. So everyone's on the same page, right? If it's a periodic chain, I have just Ta bond everywhere. And when you set E equals 0, you see that psi on j plus 1 is proportional to psi on j minus 1. Okay, so you have a solution which lives either all on the even or all on the odd sublattice of the chain, right? So let's look at starting here with j equals 0 and use this recursion law. You get minus 1 here. So psi on 2 is minus 1. Psi on site 4 is plus 1 again, then minus 1. So on the even sublattice, the wave function changes sign. And that's a periodic solution. And we know it very well. Zero energy block state. Okay, it's this wave with a wave periodicity of 4 spacings, right? From here to here. Let's go to a less trivial example. So this is the SSH model, familiar to those who studied topological insulators, the Su-Schrieffer-Heeger model. All it is 2 bonds, TB, or rather TA and TB, alternating, right? You have a unit cell of 2 bonds, okay. And in this case, psi on j plus 1 is not equal to psi j minus 1. There is a factor. This factor, let's call it R. So you start from plus 1. This wave function is minus R plus R squared, and you multiply each time by minus R, and you go in this geometric series. Let's suppose R is less than 1. This wave function decays like so, and the envelope is an exponential, right? And these are the edge states in the SSH model. And now we have the problem which we are interested by, the Fibonacci chain. Again, let's use this formula. So we start with site J0 equal to amplitude 1. And you see there's an A and a B, so this amplitude is minus R. But then here we have 2 bonds which are the same, so the ratio of hopping amplitudes is 1 in this case, so I just change sign. Here the B and the A bonds are in the reverse order, so I divide instead of multiplying by R, and so on and so forth. I hope sufficiently clear. Okay, so this is a wave function which is modulo a plus or minus factor. You have a constant raised to an integer power. Let's call that integer the height. Okay, so the height is a number, negative or positive, and it doesn't depend on the Hamiltonian, right? It just depends on what is the sequence of bonds that you have to go through to get to a certain site, okay? So the height here is minus 1, the height here is plus 1, right? You just look at the power of R. And this, if you want to discover a pattern, you want to characterize this wave function, look at it for a bigger system. This is about 1,200 sites. Oh, it's okay, it's fluctuating a lot, right? Maxima, minima. What more can we say about this wave function? Well, actually, we can show that it's a multifractal by using the self-similarity, or rather inflation transformation. Remember, I can take a short chain. If the first site has a height h, I can calculate the heights of every second site using my rule for AB, AA, or BA sequence. Then you can inflate the chain, get a longer chain, and calculate the heights again. If you do this, keep inflating the chain, you can find out a relationship between the probability distribution of them at every step. You can write it down analytically. Write down a relationship between these P of H using the geometrical properties of the chain. And long story short, I mean, if you're curious, it's all explained here. But the result is a Gaussian distribution, easy to understand, right? So the heights on a very, very long piece of chain, they are symmetric around the 0, and you can have very negative values of H, very positive values of H in this probability distribution. And so this distribution has a width which diverges when t goes to infinity. So you have this large distribution of heights. And remember, wave function is exponential function of the height, right? It's r to the power h. So these guys are going to go extremely high in amplitude, and small values are going to go to 0 with system size. And the scaling of the probability amplitude, let me just remind you, if you take a little box of width L and calculate the probability to be within that box, it's the sum of the squares of psi, right, for all the sites in the box. And this scales with the size of the box. If you're in a periodic crystal, it scales linearly with L. But if you're on a fractal set, then alpha will be some fraction, right? Now, if alpha is not constant but changes depending on where you are, then you have a multifractal. And that's what we have here. So the scaling is different. And in that, it looks, it doesn't look like, but it has the same feature mathematically as these random wave functions at a critical point in the metal insulator transition. So this is, you have extended states, localized states, and right at the transition, you have these multifractal states in the Faibus-Anderson model or similar random models. So once again, I will not enter the details, but to show that the thing is multifractal, you can compute what's called the F of alpha spectrum. The wider it is, the more inhomogeneous the scaling all over the systems. The narrower it is, the more it tends towards the monofractal limit. So if you change the TA over B ratio, you get little by little from a very broad distribution to the narrow distribution and the crystalline limit. I just put down the formulae because they're compact, and you can see that there is a solution, an exact solution to the problem. And now all the other states are multifractal as well. And we can't prove it because there's no exact solution. But we can show it numerically and perturbatively and experimentally. So this is what Frédéric here showed in this paper with the group of Fabrice Mortesagne. So they realized a Fibonacci chain using these artificial atoms, which are little dielectric resonators. So you can excite a single mode. And if you put them side by side, they couple. And so you can realize a Fibonacci array. Okay? And with this Fibonacci array, you have a strong hopping, which is this, they're close together resonators, and a weaker hopping, D, W, and D strong are strong and weak hopping, right? So that's exactly the model I was talking about. So you can actually go and measure every eigenfrequency, you can measure the eigenmode, you know, the local intensities above each of the resonators. So you have a map of the wave functions for every energy eigenstate. And they plotted that. Okay, so what they plotted was an intensity map of the local electromagnetic field, right? Intensity for every, the eigenmodes are listed here from the smallest frequency to the biggest frequency. And here are all the sites, 1 through n. They applied periodic boundary conditions by putting the things in a ring. Okay, so when you look at this, one thing you say, okay, these are not localized states, okay? The intensity is somewhat distributed widely in space, but other than this, it's hard to see any structure. So we need to think outside the box, and we need to think in hyperspace. So let me show you that picture again from like 15 minutes ago. We had the chain, which was actually the zigzag line. And a zigzag line, you can project it on the y-axis, right? Y prime axis. Atoms have a coordinate here, and you can number them by according to the position on this direction. And it won't be the same numbering as in real space. Now, why should I do this? Cyr and Mosri showed that actually it's two sites which have very similar y prime coordinate, have a very similar local environment. Their neighbors look very similar to a big distance. So they did that. They calculated the core numbers. This is the position along y prime, and this is still the energies or frequencies. And you see, it's a nicer picture, right? So this is a very beautiful picture. You see a self-similarity. It has a fractal structure, and it even has, so when you go to larger systems, you see more and more details of the fractal. And it has this funny symmetry between, if you exchange position and energy or frequency, the thing has a symmetry. So it's a very beautiful representation of this spectrum and eigenstates. And they were actually able to quantitatively do the multifractal analysis. So I encourage you to look at the paper. Okay, so let me just very quickly pass to 2D and then to experiments. You can do a very similar thing for 2 dimensions. So I want to show you this Kalugin-Katz ground state. There's an important contribution because there's really very little known for 2-dimensional systems, let alone 3, right? So again, they showed that the wave function on any position m has a factor which is not interesting, and another factor which gives multifractal properties. It's this constant r raised to a power h. That's the height function. Reminds you of the 1D. Now you can do this. So we did, our paper consisted of computing the multifractal properties of this kind of wave function. And what we can do is calculate the heights distribution and the f of alpha spectrum. So all this is described, and you can do it for different tilings. You have different values of the parameter r in the 2 cases. And the actual wave function looks like this. There are dark regions where the heights are very, depends on the value. So anyway, they're either very large or very small, negative, okay, very big magnitude, let's say. And the maxima are positive or negative, large amplitude. So this is the kind of thing we're talking about. And now let me hurry and show you some experimental work. Okay. So the question is, what does this all have to do with real quasicrystals? I want to give you 2 examples. One is a quantum critical quasicrystal, and the other is a superconducting quasicrystal. So look at them, they're horrible chemical formulas. The structure is actually rather simple. I mean, for the experts, you know, the structure is actually very neat. So you can make it in the form of this icosahedral alloy with clusters of atoms. Or by changing the composition a little bit, you can make it into a periodic system. It has the same building blocks. Local environments are very similar. So you can compare the crystal and the quasicrystal, right? For these 2 sets of. Now the heavy fermion quasicrystal, if you measure susceptibility at low temperature, these are for higher fields, you lower the field, at 0 field susceptibility is diverging. Okay, it's diverging as this power law. And resistivity specifically, they have anomalies. So this is a quantum critical compound. And if you change the pressure, it stays critical. Okay, so they called it self-tuning. You didn't need to adjust any parameters, you know, lattice or otherwise. That was a quasicrystal. So you plot the inverse susceptibility. Inverse susceptibility is 0 at 0 temperature, but not the approximant, which has still a finite interface at 0 temperature. So it's only critical if you apply pressure. So how do you explain this difference? Okay, so we had a explanation, which I'd like to tell you in 2 words. We invoke Kondo screening. So in this system, in any periodic system, rather, if you put an impurity spin, it interacting with the electrons with the antiferromagnetic coupling, it will get screened below a certain temperature and become a singlet and magnetically irrelevant, right? And this happens when you have a conduit at the temperature given by the coupling, J, of the impurity, and the conduction electron density of states, okay? Which is, L is supposed to mean the position, but in a crystal, all positions are equivalent. So there's only one conduit temperature. And you saw that the quasicrystal, you have all these funny multifractal wave functions, and so the local density of states could be different from here to there position. And so we computed using a slave boson mean field theory on a two-dimensional tiling. It was difficult enough. There are not many calculations in 3 dimensions. Then we found a power law for the conduit temperature. Okay, conduit temperature can be 0 or tend towards 0 in this quasicrystal because the density of states, remember, can be very, very small, okay, in certain areas. So spins are not screened. Not screened means that they diverge because an isolated free spin diverges is 1 over T susceptibility, and these guys are a little bit slower. So this explains why quasicrystals could have an infinite susceptibility at 0 temperature. And if you have an approximant, you don't have the multifractal states, and the things are cut off, and below a certain value of temperature, all the spins are screened. So this was one explanation, but it's too simple. You know, impurities talk to each other, so we don't really have this dilute limit. And then valence fluctuations are actually relevant for these systems, and there are works which discuss that. Okay. So let me now move on to superconducting quasicrystals. Again, the quasicrystal is compared with approximant crystals. All of them have some transition at very low Tc, 50 millikelvin. And you have the Meissner effect and a specific heat anomaly measured in this paper 2018. What about theory? So this is results obtained by our guest, Dr. Takemori from Osaka, and her collaborators. So they solved a Hubbard model. I should say that she is here for the month of June, if anybody wants to chat. So this is, for example, the calculation for the BCS order parameter in real space. You see the nice, beautiful picture, you know, which looks different. If you change Fermi energy, it will look a little bit different. And they computed thermodynamic properties. And there are other people as well who have contributed for different tilings, different models, okay? But at the end of the day, okay, so many questions. So how does the microscopic, how do phonons, if it's phonon mediated, and if so, how do they couple to the electrons, and what does the Cooper pair look like when you don't have translation invariance? How do you screen magnetic fields and so on? So it's lots to do. As I said, I will skip. I'm very sorry, but it is a rather nice topic that deserves more time than 3 or 4 minutes. Okay, quasicrystals have topological properties which are related to quantum Hall problem. Let's skip that. And just, I have 10 minutes. I have 10 minutes. In that case, I can say 2 words about this. So our colleagues in Cédezenne, down the road, realized, again, a system of resonators in a Fibonacci sequence. I won't go into what these are, polaritonic arrays. So it's like the tight binding model, not quite the tight binding model because actually it's a much more complicated Hamiltonian. What they have, though, is a system where you open gaps just as in the Fibonacci quasicrystal. And in the gaps, they observe edge states. So in this experiment, you can map the energies, the momentum, the real space positions, and so everything can be followed as a function of the parameters in the Hamiltonian. And what they showed was the edge states have a behavior which can be described in terms of Chern numbers. For each of these gaps, there corresponds a Chern number, and I really don't wish to enter into the details of how to do that. Okay, it's gap labeling in quasicrystals, so you can ask me if you're interested afterwards. So, but the point was that they did an experimental verification of the Chern numbers for Fibonacci chains. Okay, and the point is that the Chern numbers are the same, exactly the same as the Chern numbers you would deduce from this Aubry-André model. Once again, if you don't know what that is, that's a little too long for me to go into now. But the Aubry-André model is a model where you have hopping in between sites and then a potential energy, which is a cosine. If you take this potential energy and you deform it so that the cosine becomes a telegraphic kind of rectangular signal, then you get the Fibonacci model. That's basically, you can make a connection between the Aubry-André cosine potential and the Fibonacci two-valued discrete potential. That's what this figure is trying to show you, that V as a function of position can go from the cosine to this other form, and therefore, and if you can do this adiabatically, then you are showing the topological equivalence of these two models. On the other hand, Aubry-André is related to the quantum Hall problem, and that's another long story. Not too long, but still, I can't do it in 1 minute. So the quantum Hall problem is where you have a magnetic field, electron moving around on the square lattice. You know that you get a rich spectrum, and you can fix the magnetic flux and look at how energy levels are distributed. And in the quantum Hall problem, you know that there are gaps also characterized by Chern numbers. And this time, you can measure them by measuring the Hall conductivity, because the Hall conductivity is also known to be proportional to the Chern number. Okay, so this is a little indirect. So the Fibonacci chain is linked to the Aubry-André model, which is nothing but the 2D quantum Hall problem. So you can do a bunch of experiments to test these topological aspects. And this has been quite a busy area of activity for quasicrystal, not just for Fibonacci, but for all quasicrystal. So I think we're good to finish with a very brief list of new directions. And one is moire systems, which many of us here are probably interested in. They're fashionable. I'll talk about it in the next slide. Cold atoms community have been interested also because those are quantum simulators. You can do a large number of condensed matter models with cold atoms. Then there's quite a bit of recent publications on these time quasicrystals and flow-K engineering. For applications, one should say that photonic waveguides seem a very good prospect. So quite a bit of work on those. And then, last but not least, I mean, there's a very rich set of theoretical problems you can solve in statistical mechanics, traveling salesman, spin models, dimer models. I don't know much about these, optimization. Okay, so let me tell you a little bit about Moiré systems. So these were discovered a few years ago by the group in MIT. And they, I think it was an accident, really. So they have 3 layers of graphene. The first 2 layers, the bottom and middle, you have a twist angle of theta 1, 2. And the next 2 layers are twisted by a slightly different theta. So that the first 2 layers form a moiré, and the second 2 layers form another moiré, slightly different. And the combination of these gives you a quasicrystal. That's what they discovered. So they have this system, and you can play with the gate voltages and vary the parameters. And I think it's a flat band system, and it was found to have a superconducting phase. But not just the only thing. Okay, so I think these have been quite interesting to explore, these systems. You can look up some of the articles on this. So the twistronics and quasicrystals. You can make synthetically also by depositing carbon monoxide molecules, Penrose tiling. There have been attempts to artificially synthesize tilings because, as I said, most of the theory has to do with simple things like tilings in 2D. So that's this experimental paper. And now to get to cold atoms, we have our colleague in École Polytechnique, Laurent Sanchez-Palencia, and he has worked on Bose-Einstein condensates and properties in quasiperiodic potentials. So I think that's probably can be synthesized soon. And as for this group in the Cavendish lab in England, they have already shown very interesting dynamical effects coming from optical quasicrystal. This is took from their website, the picture of their setup. Okay, so finally, this example is of time-dependent system. So you can drive cold atoms in a quasi-periodic way and look at the dynamics group in Santa Barbara. Next, time-dependent systems, precisely. We continue, and there's this idea of time crystals. And there's this paper which seems to have created a bit of excitement. So you can shine lasers into diamond and excite the color centers and create something. We can make something which is varying quasi-periodically. And that's this YouTube channel by one Ben Miles, whom I don't know, but he very enthusiastic about this. So you can listen to this YouTube 5-minute talk, or even less probably. So these are some of the ways in which the research is heading. As I said, the photonic systems, those are probably the most advanced in terms of applications or feasibility. Here is, for example, this group, this is theory, and they have a way to study the topological modes in tiling. You see, you have a 2D tiling, which is the transverse section of this waveguide. So you can see how the edge modes propagate and maybe turn colors and so on. So that's a waveguide system. And this is a silicon-based superlattice where you have very good band gaps, reflectivity properties, and so on. So you can do that by realizing a Fibonacci sequence of semiconductors. And I believe that we are reaching the end. So I may have gone too fast in places, but let me just finish. I would like to thank all these people that I've worked with in the last years and have a page of conclusions. Quasi-periodic systems, as you saw, are still interesting to people. There are new results, new problems to solve. And I would say theory is still a long way behind the experiment. And in this context, I wanted to quote the famous artist, Moritz Escher. And he was fascinated by spatial patterns and tessellation, right? And he made these beautiful periodic arrays of motifs here in black and white. You see one. And he was also fascinated by dimensional paradoxes involving 3D. So you have paintings where you look at it, it looks realistic, except then you realize it can never be made in our world, at any rate. And he was even an inspiration to Penrose for the invention of his tiling, I believe. So this is a quotation. So he was speaking about crystals, which he was fascinated by. Such laws take the breath away. They're not discoveries or inventions of the human mind, but exist independently of us. So in a moment of clarity, we can discover that they are there and take them into account. So for me, the message is quite clear. We should continue to investigate quasicrystals and other aperiodic systems and try to understand them and how to use them. And so with that, thank you for your attention.
Okay, well, thank you very much, Anu, for this beautiful and very detailed talk, yet very pedagogical. Do we have any questions in the room? Oh, yes.
I had a question on slide number 41, which, yes, which. Yes, so here, this is probably something I did not understand well. So here the lattice is a quasicrystal. And so does it mean that a lattice which is a quasicrystal and a lattice which is a regular periodic crystal give different results even in the macroscopic limit?
Can you explain a little bit why you stress macroscopic?
No, so what I'm saying is that so basically if this model was worked on a lattice which is a periodic crystal, then the susceptibility, the macroscopic susceptibility would have been different, right? And is there a simpler to understand why? Because normally this is what is a bit difficult to understand why over a macroscopic limit, the thermodynamic susceptibility would vary depending upon the lattice order.
I see where you're going. All right. For me, the situation doesn't have to do with so much with the k equals 0 and the k not non-zero aspect. I think that's what you mean, because this is the k equals 0 susceptibility for the test. But it has to do with the subset of spins which are screened and another subset which are not screened. And they are not arranged in a periodic, they would be arranged in some complicated way, right? So all we want for the bulk susceptibility is for there to be some finite fraction, small, but they would diverge, give rise to that divergent tail. So I think in a periodic crystal, what happens to one impurity happens to all the impurities. This is the difference. So either all of them are screened or none of them are screened. But in a quasicrystal, you have both kinds, right? The screened and the non-screened. That's the simplistic picture we have.
Say that there is also quasiperiody in soft matter.
Yes.
And is there any quasiperiody in biology, for example? Quasiperiodic pattern in biology?
Okay. One funny answer might be that people play with DNA, and we have made DNA quasicrystals. I think those exist, but as a toy. But I'm not aware of any genuine biological system which would be quasiperiodic. No, I have never. Because some people confuse, I think, symmetries with the long-range quasiperiodicity. So you can find five-fold symmetry in nature, but that doesn't mean that there are biological, so I don't think so. The answer is maybe Jean-François, he has studied pilotaxy. So indeed, you can find in certain plants, right, the Fibonacci sequence, things like this, or other spirals. Right. Sorry. So I take back what I said. So in the plant world,
beyond Fibonacci pilotaxis, is there any 2D quasiperiodicity? More 2D quasiperiodicity.
Related to quasiperiodicity is the organization in phyllotaxy is quasiperiodic.
Yeah.
You have some kind of grain boundary which are organized in a quasiperiodic way.
Yes, I had a question. So the chemical formula are huge, which means that describing this with the theory, so that there are the approximants, but then is it possible to describe them in an exact way without the approximant, which means that you will find the minimum energy of a huge thing accurately?
okay, so your question is that in principle, can you give a prescription to locate all of the atoms?
Yeah.
One of those also extremely interesting questions from the very beginning. So the question was, where are the atoms? And yes, so there are models. And precisely that's what the early quasicrystal of Shechtman, you could not really, because they were very disordered. But these guys, they are rather well described by structure models. So you can say exactly where the atoms of ytterbium, where the gold and, okay, there's still a little bit of stochasticity, but the gold and aluminum can interchange positions. So but you can give the chemical or rather the structural details of where each of the atomic species is sitting. So it can be done, and I have somewhere a picture of the details of this picture here. To avoid cluttering everything, is only showing the pink atoms, which are ytterbium. And all the matrix of gold and aluminum is in the blue stuff. Okay, but I can show you if you're interested that they are polyhedra of atoms, and the polyhedra are arranged next to each other, and there are some atoms between those polyhedra. It's complicated. So for theoretical modeling, it's very hard to do. Certainly ab initio, I don't think it's really worth it, because the band structures really has hundreds of atoms per unit cell, and a difficult problem. Even for these, right? Even this is hundreds. Yeah.
Thank you.
Thank you for the talk.
I have a question for this Fibonacci chain. Is it topological? And if yes, can you assign some topological number to it? And how you do it in the moderate periodicity, let's say?
Okay, so forward topology part. Okay, so when you take the Fibonacci chain, oops, that's the one I want. In the Aubry-André model or the Fibonacci chain, either of them. If you make a finite sample, so in this, there's this irrational parameter B, in the Aubry-André model, it's an incommensurate. But you can make it a rational number, and then you have a unit cell, which is some size, and diagonalize the Hamiltonian, right? Mm-hmm. You get a spectrum, which is this guy. So you get from, it's just integrated, that's your state. So you go from one band, another band, another band, and in fact you can't see the gaps, but there are gaps everywhere.
Okay.
And that's for the Aubry-André, and you see for the Fibonacci hopping model, very similar. So you have gaps here, 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 okay? So are you seeing that in the picture? So they have gaps in the same integrated density of states is the same. So that and within the gaps, you can compute what is the Chern number.
Mm-hmm. So it's...
So this is the topological invariant associated with the chain. Now, what it meant was not understood. What this Chern number should mean is something that the experimental people, like the group of Jacqueline Bloch, showed. They said, okay, that number is actually related to the number of edge states.
All right, but
so you have edge states which they were able to measure.
Is it really like a so it behaves like a sort of 2D system? So that's a Chern number?
Yeah.
Okay.
Yeah. It
okay.
behaves like a 2D system.
Okay.
But you cannot do the same calculations and you cannot do the same experiments. For example, Hall conductivity.
Yeah. Okay. Thanks.
And the thing is that now we can look at the higher dimensional quasicrystals, ask what is, maybe there you could measure transverse response functions.
Okay, well, I think that's a lot of questions. So thank you very much, and see you next month for last seminar. Thank you, Anu.